Hello everyone, I am N. Shivakumar, Department of Chemistry, Kamaraj College of Engineering and Technology. I am going to present the topic about potentiometric titrations. So normal volumetric titration we need an indicator, but in the case of potentiometric titrations there is no indicators are used. So let's see the overview of the presentation. So introduction about the potentiometric titration, then terminology, then electrode potential and EMF, then principle, then types of potentiometric titrations, and then precipitation titration, AgNO3 versus NaCl, redox titrations, ferrous sulfate versus potassium dichromate, advantages and applications of the potentiometric titrations. So this is the introduction. So in this introduction we have to discuss about the potentiometry. So normally we can call it as potentiometry. Potentiometry is a chemical titration technique that does not use a color indicator. So we may not use the indicator as a color. So this is the first point. Then second one is we may call it as potentiometric titrations. So instead of potentiometry we may call it as potentiometric titrations is there another name for it. Then this technique measures the potential of the analyte with the help of electrodes. So we are using two various electrodes, one is reference electrode as a Calomel electrode and another one is indicator electrode. So by the indicator electrode we have to measure the analyte which concentration of the electrolyte solution. So here the analyte is nothing but the electrolyte solution. So it uses two rods, that is nothing but an indicator electrode, metal ion electrode, and another one is reference electrode. So metal ion electrode, instead we have to use the platinum electrode. In the silver concentration solution, if we are using as an analyte, we can use the silver ion electrode. So let's see the terminology about the potentiometric titrations. So here we have to introduce the concept about the titrant, analyte, and another one is equivalent point. So this is the basic terminology which is involved in the potentiometric titrations. So first case is titrant, a solution used in titrant whose concentration is known to us, and then so it is added to the another solution. So we have to measure the unknown concentration of the solution. So that is called the titrant. Then second one is analyte. So analyte means the solution concentration it is unknown. So that is called the analyte solution. Then third one is equivalent weight. So equivalent point. So in this case the point in potentiometric titrations at which undergoes the sudden change in it. So in EMF that is called the equivalence point. So where we have to find out the equivalence point, that is called the end point. So these are all the basic terminologies when we are moving into the potentiometric titrations. So next one is electrode potential. So we may know that what is mean electrode and electrode potential. So electrode means normally it is a metal rod or strip, it is called the electrode. So in this electrode potential means, so the potential it will be created in the electrode, that is called the electrode potential. So single electrode potential and another one is standard electrode potential. So single electrode potential it is normally denoted as capital E. So it is nothing but it is a measure of tendency of the metallic electrode to lose or gain its electron when it is in contact with the solution of its own salt solution. So that is the electrode potential. So normally it has the tendency to gain or lose electron when it is contact with the solution of its own salt solution. So here second term is nothing but standard electrode potential, that is E naught. So here it is a measure of tendency of the metallic electrode to lose or gain the electron. So when it is in contact with the solution of its own salt, so at 1 molar concentration and 25 degrees Celsius. So here concentration of the solution as well as the temperature are specified. So that is called the standard condition, that is specified as E naught. So next we have to discuss about the EMF. EMF is nothing but electromotive force. So what do you mean by electromotive force? So here the electromotive force is defined as the potential difference may be arise which causes flow of electron from one electrode potential to the another electrode potential. So we may say that that's a higher electrode potential to the lower electrode potential. So EMF of the galvanic cell can be calculated with the relationship E naught cell, that is equal to E naught right hand side half cell minus E naught left hand side half cell. So here EMF is defined as standard reduction potential of the right hand side electrode minus standard reduction potential of the left hand side electrode. So this is called the EMF. So normally the potentiometric titrations are measured by the EMF. Unit is volt. So here this is the basic principle of the potentiometric titration. So potentiometric titrations are the potential difference between the two electrodes used to form the basis of the potentiometry principle. So here the addition of the titrant leads to the change in the ionic concentration, so causes the potential differences. The indicator electrode measures the potential differences and the reference electrode has a potential, so in that value and remains the stable when dipped into the sample solution. So this is the main concept. So we are using the two various electrode, one is called the indicator electrode and another one is called the reference electrode. Reference electrode, that is a stable one. So here the metal ion concentration, it can be reflected in the digital potentiometer. So here we are using the salt bridge. So salt bridge is nothing but it is made up of by the saturated KCl solution. It is a paper strip or it may be a connecting material. So that material, it consists of the that it will provides the electrical continuity of the solution, it eliminates the liquid junction potential. So for that this is a main function of the salt bridge. The salt bridge is a device used during the potentiometric titration to avoid the intervention of the analyte solution with the reference solution. So next we have to discuss about the basic concept about the potentiometric titration. Normally all the potentiometric titration which is depends upon the concentration of the solution. So EMF which is depend upon the concentration of the solution. So here which the electrodes are in contact, therefore the electrode reaction is M metal ion plus N electron, so it forms the metal. So as the concentration of the Mn2 plus, as the EMF of the cell also changes, it will correspondly. So next the calculation of the total potential differences. So E cell is equal to E indicator minus E reference potential difference on the EMF. So E cell is equal to E indicator minus E reference plus E junction potential. So here E cell, it is nothing but potential of the whole cell, then E indicator is the potential of the indicator, where E reference is the potential or electromotive force of the reference electrode, then EJ, it is potential at the junction across the salt bridge. The measured electrode potential, it is depends upon the concentration of the metal ions present in the indicator electrode, that is in contact with the indicator electrode. So these are all the types of potentiometric titrations. So normally the potentiometric titrations are various different types, that is acid base titration, and another one is redox titration, then precipitation titration, complexometric titration. So first of all, acid base titration means titration of the HCl and NaOH can be done by potentiometric titrations. So with the help of the standard acid, so it can be carried out, that is called the acid base titration. So redox titration, potentiometric titrations are it being titrated with the halide ions with the KMnO4 using a platinum electrode using the calomel electrode. The next one is complexometric titration. The complexometric titrations are the metal ions are determined in the analyte and the membrane and the electrodes are used, that is called the complexometric titration. The next one is precipitation titration. So where it being formed a precipitate. So in this the precipitate is formed as the name suggests like that. So when the addition of the titrant no longer being formed as a precipitate, that point it will be noted as the end point. So this is the complexometric titration and the precipitation titrations. So this is the entire setup of the potentiometric titration. So here this is the burette. So it is taken the titrant which is taken in the burette. So then the two electrodes are connected. So one electrode, it is called the indicator electrode. So this is maybe a platinum electrode or silver ion electrode. Then again the another one electrode is there. This electrode is called the saturated calomel electrode. That reference electrode, it is called as a reference electrode. So here the two electrodes are interconnected with the digital potentiometer. Then there will be analyte solution, which is solution we have to test and we have to know the concentration of that particular solution, that is called the analyte solution. So here the analyte solution is taken in the beaker, then it is provided with the magnetic stirrer. So this is the entire setup of the potentiometric titrations. So normally the potentiometric curves are like this. So here we are getting two different graphs are merged here. So here this is the this indicates the that is the precipitation titration. So that EMF going decreases drastically, and from that we cannot find out the equivalence point exactly. Then we have to draw a graph. So in this graph we are getting the value that we have to get the equivalence point. That equivalent point will get the unknown concentration of the solution. So this is this graph, it will be plotted volume of the solution versus the EMF. That is we have to draw the another graph, that is volume of the solution versus delta E divided by delta V. We are getting the curve graph. So here this is the precipitation titration, one of the potentiometric titration we carried out. So AgNO3 versus NaCl, the known amount of AgNO3 solution is taken in the beaker as a analyte, and then indicator electrode we are using as a silver ion electrode. So here we are using an indicator electrode as silver ion electrode because we have taken the analyte solution as a silver. So here in this, it is connected with the reference electrode, calomel electrode. The cell is connected with the potentiometer, that E cell is being determined. So when AgNO3 solution is being titrated with the sodium chloride solution, so it is taken in the burette, the EMF is going decreasing as the Ag plus concentration decreases. So here AgNO3 plus reacted with the sodium chloride, it will forms AgCl as a precipitate, and it will forms the NaNO3. At the end point, EMF suddenly decreases. After the end point, there is no precipitation will be created, and then a noticeable change in the potential is noted. So this indicates the precipitation titration. So let us see the graph of the curves of the potentiometric titration. First graph represents the volume of sodium chloride versus EMF. So here the EMF being drastically decreases because of the precipitation formation. So from that we can note the equivalence point. So the equivalence points cannot be noticed clearly from the first graph. So for that we have drawn the derivative graph. So here volume of sodium chloride, it is drawn against the delta E by delta V. So here there is a graph we are getting. So we are getting the excellent we are getting exactly that equivalent point. So this is called the derivative graph. This is delta E versus delta V. Delta E means the difference in the EMF, where delta V is the difference in the volume. Then we have to draw the graph against that. So according to the figure, so we have to draw the delta E versus delta V, we are getting the exact endpoint. Then second titration, it is called the redox titration. In this redox titration, ferrous sulfate versus potassium dichromate. So ferrous sulfate solution is taken in the beaker, and the indicator electrode it is inserted. Here we are using the indicator electrode as the platinum electrode, and it is the reference electrode is also connected, that is calomel electrode, to form a galvanic cell. So the cell it is connected to the potentiometer, and it is E cell is determined. So here this is the reaction, the cell reactions, potassium dichromate, and it is reacted with the sulfuric acid. So here we are taking the potassium dichromate, and it is an acidified medium, it will forms the K2SO4 plus chromium sulfate, and then 4H2O plus nascent oxygen. This nascent oxygen is reacted with the ferrous sulfate, and in the presence of the catalyst it will forms the Fe2SO4 thrice and along with the H2O. So then next one is, so here we are the same reaction, it can be we are written as a overall reaction, and there will be ionic reactions are there. The ionic reaction represents the reduction half cell, and another one is oxidation half cell reactions. So this is the ionic reaction, the total ionic reaction is represented. So here the redox reaction, iron 2 plus it may be oxidized to iron 3 plus, and the same time we are getting that the chromium has the 7 plus oxidation state, it is being reduced into chromium 3 plus oxidation state. So there are two cases are happening. So only we have written as a reduction half cell reaction and then oxidation half cell reaction. So here this is also the two graphs we have drawn for the potentiometric curves. So here you can see that differentiate between the precipitation titration and then redox titration. In the precipitation titration we are getting the graph, it is a like a opposite direction. So here in that volume of potassium dichromate versus EMF, so initially it may be increases. So if you are observed in the precipitation titration, the volume it can be decreases, here it may be increases because of the condition. So here EMF will be increases, and drastically it may increases, and we are getting the graph. So second one is delta E versus delta V. So here we are getting the steep curve. So from that we can find out the equivalent point exactly. Then this is we have to draw between that delta E by delta V, we are getting the graph, the slope from the slope we can find out the unknown concentration of the solution. So let us see the advantages of the potentiometric titrations. So that the necessary apparatus required is cheap and then it is easily available, that's a main advantages. Then this method is used for the colored solution. Then the fixing up of the endpoint, and then when compared to the titrations in which indicators have to used as the fixed up endpoints. So the exact endpoint will be noted, and when we are comparing to the other titrations, so this potentiometric titrations have the fixed endpoint. Then very dilute solutions can be titrated with accuracy, and then several components may be titrated in the solution. So these are the main advantages of the potentiometric titrations. Then let us see the applications of the titration. Mainly it is used in the clinical chemistry, and then analysis of metal, then wastewater treatment, it is a main important one, then analysis of cyanide, ammonia. So these kind of things we can easily analyze by the potentiometric titrations, and it is used in agriculture for the detection of the elements in soils and soil nutrients and fertilizers. So these are all the main applications, and it is used for the detergent manufacturing and then food processing. So various different types of applications we have done by the potentiometric titrations, or we can call it as a potentiometry. Thank you.